All right, good afternoon, everyone. Today is the June 27th issue of the HamSCIence Zoom call. I know for sure we won't have Dr. Fischel with us today. I believe he and his wife are at the hospital expecting a new baby. So yeah, they sometime this morning, Nathaniel texted a few of us that he wouldn't be on the calls today because it looked like it was time. So let's hope everything is going well for them.
I saw the
We may have a new
Facebook post.
HamSCIence member soon. That's all. Or maybe we already do. Who knows?
Yeah, I saw the Facebook post. Look ready to go.
So good. All right. Couple of things today. I would like to share a couple of pictures and tell a little bit of a story about my trip to the Nobel Museum. Hope everybody appreciates that. It's good to see Ed back from his travels in Italy. We got a fast-talking guy from Palermo now, and not just from New Jersey. So that helps quite a bit too. And welcome everyone. We definitely got a quorum. We've got 13 of us on today, so that's a good thing. Is there anything anybody wants to add to the agenda? We can do it later. We can do it now, but I'll take a couple notes. Nope. Okay, let's get ready to go then.
I have something small, but never mind.
Sure. Okay. You want to do it now, Mary Lou? Or you want to wait?
I'll wait.
Okay.
Go
I'll
for it.
make a space holder for you. All right. Let me share my screen real quick. Desktop. All right. Monsters. Numbers. So this here is actually the Nobel Prize Museum in Stockholm, Sweden. I was fortunate enough to be there, I think maybe 3 or 4 weeks ago. It's easy to find. It's right near the Royal Palace. If you're looking for the Queen or the King, you just go the next block over, and here's the Nobel Prize Museum. It's not particularly large. It consists of 2 areas. This is about 1/2 of the museum. And it consists of these cabinets, which have stories about the various Nobel Prize winners, whether it's mathematics, physics, chemistry, economics, the Nobel Peace Prize, and I think medicine and physiology is the other possible source for a Nobel Prize. But anyhow, you could go through these cabinets and read about the people who've gotten one over the years. The interesting thing, each of these people donated something to the museum that they felt was significant to them, not necessarily to the research directly, but significant in their lives that helped them do whatever breakthrough it was that earned them the Nobel Prize.
What sort of things did they give?
Well, I'm going through a couple. I'll show you a couple. You notice the bicycle up here on the upper left. That thrilled me. Somebody put their bicycle there. One woman, I forget what she won it for. She put in an old, nearly empty jar of peanut butter because as she said, she did her research and she stayed up late at night. That peanut butter gave her sustenance, and that and that was a big deal. So yeah, there's a whole variety of things, and I want to show a couple of them. Let's see here. Let's see if my computer will cooperate.
Did they have anything from Einstein?
Well, he was obviously mentioned and had some pictures, but I don't know that he was mentioned specifically. Let's see. Okay, so this guy, let's see. This I found was interesting. Was a model that he kept in his office of the first very early electric car. And what this guy had done, this Ben Feringa had done, was created a microscopic sized motor. If I remember, there was something the thought was to put it into the human bloodstream to help with drug delivery or other medical issues. But somebody had given this to him. That inspired him to develop this microscopic motor, and he won the prize, and that's what he donated. Let's see. The next one. I'm going to try this again here. Okay. I was thrilled to see a sample of an early blue light emitting diode, just because I remember it as a kid playing with my Radio Shack electronics kit and having plenty of red, green, and yellow LEDs, but never blue. According to this little blurb here, was invented in 1978, but it was well into the 1980s where they became practical and helped us. Now we have white LED lights, which of course are everywhere. So I thought that was a pretty significant something or other. The test cell for the early lithium ion batteries. Where would we be today without lithium ion batteries? when they donated that. This guy, Robert Wilson, won a prize in economics. He was talking, his research had to do with how auctions are conducted and how people act. And one of the examples they used was the auction of the VHF and UHF frequency spectrum when the US moved from analog to digital TV. In fact, they actually had a spectrum chart up on the wall. But more interesting to me was this, his calculator he donated. I use one of these things every day. That's my favorite calculator. It's an HP 15C. I know millions of other people have the 12 version, the financial version, or maybe the 16C for programmers and whatnot. So he donated his pocket calculator. And of course, and I thought this was really interesting too. This gentleman here, Didier Queloz, is an astronomer. And apparently he's the one who discovered the first exoplanet orbiting a non-sun star, if I get that right.
Yes, but he had a partner.
Well, what I thought was interesting is that he was a doctoral student, and his supervisor had to go out of town. And the supervisor gave him the key to the observatory, and that's where Didier made his observations, which eventually led to the discovery of the exoplanet. Well, what made me think about this, I know I see it from Nathaniel all the time. I'm sure you, Mary Lou, are the same. I know Gareth's not able to join us today. I'm sure he's the same. But you don't have to be an older, more grizzled, 20, 30, 40 years in your field to make these discoveries. I mean, this guy was a doctoral student and went and did a pretty significant something. So I think I see Nathaniel bring how many students he brings to different conferences and that sort of thing. And I think the encouragement of, I guess you would say, the younger scientists is really something to see. And this story really brought that home.
Do you know the story about Jocelyn Bell Burnell and Joe Taylor?
No.
Oh, I'll tell you that at the end. Go on.
Okay. So there's Didier. Of course, it wouldn't be proper if I didn't have at least one picture of the slide rule, right? That's got to have one of those. But what he used this thing for is when Sputnik was up in 1957, he was working on calculating the trajectory soon after of satellites and rockets. It was kind of a hobby interest of his, apparently. But I guess I don't wish I'm any older than I am, but I do wish I would have been alive when Sputnik was up and I could have listened to that. That would have been the most fascinating things I can possibly imagine. I'm very jealous of all the people who today can say that they did that, tuned into Sputnik. So this is kind of the grand finale. This is what I really wanted to get to. They had a whole case dedicated to the visualization of data. I mean, how many of us in HamSCI, or not me necessarily, but the rest of you, are involved in visualization of scientific data? And if I can zoom in on this thing, I hope. I would like to read what he's got on this slide here about visualization. Of course, it's probably not going to work. Let me try this again. It's really giving me fits here.
An interesting book on the topic, and actually there are a number of books, is by Edward Tufte, Tufte, on the visual display of quantitative information. So,
I love that book.
Yep. I've met him a couple of times.
Me too.
Good guy.
He is. Got great ideas.
Okay, for some reason, naturally, the picture will not load. I don't know why my screen share, I suppose, should be working. Let me stop sharing, see if I can bring this picture up.
While you're doing it, Gary,
yeah.
Anecdotally, okay, all the prizes are given out in Stockholm with the exception of the Peace Prize, which is given out in Oslo at the City Hall. And it goes back to the long-standing love-hate relationship between Swedes and Norwegians, which reminds me of an old story. And let's see if anybody has the answer here. Do you know how to save a Swede from drowning?
Go for it, Ed.
Good. If everybody said no, the answer is good.
Oh.
That's the best Norwegian joke I have. So. And you can use it now that I've told it to you.
I say I spent a lot of time in museums over there, and most of them were dedicated to war and conflict, going back to the 13th, 14th, and 15th and 16th century. It's a wonder how the human race survived. I mean, we're still doing it today, right? We haven't learned our lesson. But anyhow, on the scientific display of data, a picture can sometimes say more than a complicated explanation. Translating large amounts of information and complex structures into coherent images is very important in science. So there you go, Kuldeep and others that are working on visualizing our data. You guys are right on the top. The Nobel Science Prize Museum recognizes your work, so good for you guys. You had a Joe Taylor comment, Mary Lou?
Okay, this is I think it's kind of a long story, but I think it's a very interesting story. Do we have other real business we ought to do first?
No, I think we're good.
Okay, so let me tell you the story. So in 1967, pulsars were discovered by Jocelyn Bell Burnell. She was just Jocelyn Bell at that time. And what had happened is that she had built, so this is her PhD thesis, she had to build a very large array of, I believe they were dipoles, very small ones, in a field in England, and the apparatus altogether then would listen to radio waves and try to find out some things at some smaller resolution than anybody had ever done before. And so she did that, and in the first couple of runs of discovery, so she found 4 items which she called bits of fluff. So this was just a continuous time sequence. There was no steering the apparatus. The Earth turned, and as the Earth turned, things went above it. And if any radio waves were coming from them, they detected them. And so you just got a long wiggly line that went on for 24 hours and then started over again. And so it was a lot of reams and reams of chart paper spitting out of this apparatus. And the bits of fluff were that, they'd go along, there'd be noise, and then there'd be a lot of noise together that kind of made a square block of noise for several seconds. And then it went back to just plain old noise. And so she had originally thought that some piece of fluff had come off her sweater. I mean, this was England in the wintertime. Some piece of fluff had come off of one of her sweaters and got caught on the pen point of the chart recorder, and then drifted off, got off. But she looked at it and there didn't seem to be lint flying about near the machine. And then she noticed that these 4, or most of the 4 at least, repeated the next day at almost the same time, but not exactly the same time. And then she looked again the next day, and again they repeated, again 4 minutes different. And so if something is 4 minutes different, what it is it's celestial, it's not terrestrial. So there's something in the sky. So stars, rise 4 minutes earlier every day. And so there was something in the sky at some position that was right overhead of this machine, this array of receivers at that time, and it moved with the stars. It did not move with the Earth. So there was something in the sky. And then what she did is she said, okay, well, this is sort of intriguing. When this thing comes around again, I'm going to increase the speed on the chart recorder. So instead of going, it's going to go whoop and spread it out for whatever, 10 seconds or whatever it was that it was visible on the chart. And then it became clear that this thing was a sinusoidal variation. So, it would go from noise to a real sinusoid and then stop and go back to just noise again. So this something in the sky, a celestial object, was pulsating. Some star was pulsating. So it was pulsating radius. She called it a pulsar. And she and her advisor then started to look at this more carefully. And at first, of course, they thought it was something intelligent. And so they called it LGM. So there's LGM 1, 2, 3, 4. And that was, what LGM means?
Little green
Little
men.
green men.
little green men, of course. Why ever they should be little, I don't know. Anyway, so and then eventually they found really discovered this stuff and realized that pulsars were not just ordinary stars, they're rotating neutron stars. And one of the people I was working with at the time was the one who just, hypotheses. I know what those are. Those are rotating neutron stars. That's Tommy Gold at Cornell. Anyway, so then they eventually got the Nobel Prize for that, or rather, he got the Nobel Prize and she was not listed. And there was an outcry from that because she had done much of the work. But what the rationale was, it was not that she was a woman, but rather that she was a graduate student. And graduate students didn't get awards like this. So that's why it's pretty interesting that Didier Queloz got listed on this because he's a graduate student. It didn't really matter who actually did the work. The advisor got the award. Okay. So meanwhile, before this recent one with the exoplanets and the 1960s with the pulsars, there was Joe Taylor. You all guys know who Joe Taylor is, right? So somebody tell me who they think Joe Taylor is.
He's a Nobel Prize winning physicist for it was detection of pulsars as well, wasn't it? Using the Arecibo Observatory, was that it?
Right, and what he found, he and his graduate student, Pulse, found that there were two pulsars in orbit around each other. So it's hard enough getting one, they're unusual. Getting two of them and in orbit around each other, woohoo. So it's a rather unusual situation, and they studied that one really well. And the interesting thing about that set, well, you really haven't told me who Joe Taylor is to you, though, other than that.
WSJTX.
Yeah, that's who he is. Tell me about him. What do you know about that, David?
Well, he used his knowledge of low bit rate encoding to come up with Whisper, FT8, and all these other things.
Yay, Whisper! All right. Anyhow, so Taylor and Hulse found this, by searching around, accidentally stumbled upon this binary pair and monitored it for days and days and days and days, and discovered that the sinusoid of its variation was changing its frequency. And otherwise, these pulsars were rock solid to 8 decimal points, that sort of thing. They're the best clocks ever and very repeatable. But this one wasn't, and it was changing the frequency. So that was the puzzle. And then they just their hypothesis that they checked out was that this is the first indication of gravitational radiation, which meant that, which had been predicted by Einstein in the early 1900s, that if you had two really massive objects in a close orbit, the orbit would shrink and they would in spiral, and doing so would send out gravitational waves, which is a new kind of energy. And so they were able to show that that's what was happening in this case. Anyway, years before this, Joe Taylor had said, oh my God, if I ever get the Nobel Prize and a graduate student is involved, the graduate student is getting their name on this thing with me, by gum. I want to tell everybody that. And so the Nobel people went, oh, okay. So it's Joe Taylor and Hulse. And he's Russell Hulse. He's going to get his name on it too. And so it happened that way. And then, but there were two little, I think, interesting tidbits about this. First, when Russell Hulse got his PhD in physics, he then went off and got a real job. Aha! He didn't stay in academic physics. He went off and got a job of industrial sort. So then, when they got the Nobel Prize, evidently the Swedes call you at like 4 o'clock in the morning and wake you up and say, "Hey, you got the Nobel Prize." So Pulse is sleeping and he gets this phone call. "Hey, you're getting a Nobel Prize." And he went, "Oh, this is a joke." And they said, "No, no, for real, you really are." And convinced him. So he hung up and he thought, "No, I can't do that. If I leave the phone on the hook, the press is going to call me." So he took the phone off and put it beside and let it just be a busy tone, right? And he went to his library, to his study. He got his PhD thesis and he read it from cover to cover because he had forgotten a lot of the details because he didn't do this anymore. So he read it from cover to cover and remembered everything, put the phone back on the hook immediately. "Hello, this is so-and-so reporter. I want to interview you." And he says, "Oh, yes. What are your questions?" And he did really, really well. And then he went to Stockholm and got the Nobel Prize and everything. But I thought that was very clever of him to do that. And I imagine this is all written up, but I sat next to him at a banquet once and heard this from his mouth directly. So this was the story. So then, that was number one. Number two, Joe Taylor invited Jocelyn Bell to be his guest at the ceremony. And he took her to Stockholm for the week of parties and whatnot, whatever they do, so she could experience that part of it, even if she didn't get the Nobel Prize. I think Joe Taylor is a true gentleman. That's my
Sounds
story.
like he's a class act for sure.
He is a class act, right? So I don't know him. I've talked to him a couple times though, and he is a real class act.
Yeah, he
So-
was a speaker at our club, Mary Lou.
I
when
should
he-
have
when he-
come. You should have invited me.
There you go. Well, that was a while back. Actually, he used our club as a prototype to introduce FT4. And he's just a regular guy. I mean,
He is.
what with us
right?
for pizza afterwards. It was really great. So,
He did speak at the ARL 100.
yep.
Talked to him then.
Yeah, we did try to get him as one of the keynote speakers at the HamSCI workshop this past spring, and he said, he and his wife aren't into traveling so much and that sort of thing nowadays, and he preferred to stay closer to home. So at least we gave it a shot.
Yep. I have a secret to get him as a speaker because I know what he won't talk about. So ask me often. So
So can we do this? Can we make this happen, Ed?
sure.
Yeah, I talked to him. I used to go to Princeton, so I talked to him at Princeton at one point. So
Yeah, well, given that we're
We'll talk
using
on
this
Wednesday.
whisper,
Well, yeah, who knows if the HamSCI, wow. I just got breaking news from a text from Nathaniel. Our DAISY 2 grant on the magnetometer HF VHF receivers is being recommended for funding. So that's moving along. So that's big news. Second big news, baby could be here within an hour or two. So
very good. Very
the
good.
DAISY grant was ahead of the baby in the text, but I don't think that's significant.
Not a priority, right?
Yeah, I hope Rachel doesn't see it that way.
Yeah, exactly. So, but apparently there's some more updates needed, and that's what he's trying to get done. But nobody's on the call today from there. So, okay, good. That's a good story, Mary Lou. I appreciate that. It's in some ways times change. There was a long obituary about a female surgeon today in the paper, and about all the fantastic work she had done pioneering different things in colorectal surgery and pancreas cancer research and that sort of thing. And she said she fought a lot of battles early in her career because that's the way she wanted to go, and it wasn't felt that female physicians should be doing that sort of thing. So she proved them wrong. So good for her. All right, moving on a little bit. I know last week we had some discussion between Mary Lou and Gwen. We were privy to on some of the 25 megahertz, I think it was, propagation on Eclipse Day. And Gwen, you've got some more information you want to present on that, I believe?
Yeah, just a little bit of work in progress. There's no no analysis yet, but I've been setting out my thoughts about what to look for in terms of the propagation. And I think Gary, this is so apposite when you showed from the Nobel Museum about visualization. Well, I think Mary Lou put up last week the graphic, the visualization. And then the challenge is then, what on earth is that showing us? So it's a very compact method of showing Doppler. But what on earth is going on in the image? And in particular, Mary Lou, it was the 25 megahertz image. And, we've got a Doppler, sharp Doppler, and we've got a gap. We've got a diaphanous or fuzzy change in Doppler that's much weaker. And if you look really close, and I'm not sure you can see it on the screen, but right before the fine red trace Doppler ends, there's this little squiggle. Can you see a little squiggle?
Yes.
Yeah. And even smaller squiggle at the start of the trace when it comes back. So those are stories
Can you make this bigger? In any way, can you make it?
Yeah,
bigger?
Here goes. Here goes.
There it is.
Okay, you see that squiggle?
Looks like
Yeah.
part of a clock.
Oh, yeah. Okay. So what
almost call
is
it
that
ominous.
squiggle? And there's a smaller squiggle here.
Oh, yeah.
It's bi-valued as it comes back. So what I've done is to look at the image and then, with a little modicum of knowledge about propagation, just setting out really the methodology before some analysis. And so I speculated last week that the fuzzy part, the weak fuzzy part, is 2-hop side scatter. And so the strong, fine, thin trace is the 1-hop path on 25 megahertz from WWV to Nathaniel. And there's the 1-hop midpoint, well away from the total eclipse. But absolutely fascinating is that 2-hop side scatter, and you can get an approximation for where that happens by drawing arcs of just over the path length from WWV to Nathaniel. So a path length out here a little bit, New York way. And you draw 2 circles, and where they intersect, that's a first guess at where the side scatter happens.
Where's the circles? I didn't understand that bit at all. Say again.
Okay, so maybe some of this is useful because I need to go back and reorder perhaps. So we can do a ray trace. WWV with sunspot number 103, and we have ray landing spots at Nathaniel's location. Yeah, we okay with this?
Mm-hmm.
Yeah, so simple 2D ray trace from PyLab, which Nathaniel makes available to us all. We have 1-hop propagation. Now, if I decrease the sunspot number a little bit as the eclipse happens, that 1-hop ray goes overhead Nathaniel and doesn't land until New York State rather than Pennsylvania or out in New England. So Nathaniel's station is in the skip zone. So the closest the spots are to Nathaniel, to his east, Nathaniel's in the skip zone. So let's say, right, rays are landing at, say, 2,600 kilometers away. So we can say, well, okay, so to a first approximation, if we draw a circle of 2,600 kilometers radius from WWV, get our compasses out, and draw an equal radius circle from Nathaniel's location, where they intersect, rays can travel there from WWV, and a ray from that location can travel back to Nathaniel. So this is the likely path of 2-hop side scatter from WWV. Part of it is out over the Gulf of Mexico, Yucatan Peninsula, and then there's some backscattering that just happens. Part of the backscattering ends up back at Nathaniel. And the midpoint of that path is right on the center of the eclipse. And it happens much earlier than at the 1-hop location. And we also get another intersection with the ionosphere out here. So it's a lot to delve into, which is why there's a lot of words here. Now we can do ray tracing now in 3-dimensional mode. And this is what I've done here. So all of these little black dots are where ray landing spots happen from WWV. So they land, there we are in New York, to the east of Nathaniel. There's no 1-hop propagation to Nathaniel. And Nathaniel, if he had a transmitter instead of a receiver, his ray landing spots would be the magenta spots. So where you could have backscatter, side scatter, is where those intersect. You won't get any side scatter out here over the Pacific. There's no intersection, or over this part of the Atlantic, the mid-Atlantic bight and so on. But you do get this intersection in the Gulf of Mexico. And then when you contour the product of the number of ray landing spots, you get this sort of image here. And that is the 3D ray tracing's best estimate for where the scattering happens.
In the
So
Gulf of
it's-
Mexico.
Gulf of Mexico, yep. Yep.
Now, what is the mechanism that causes the side reflection from there back to Nathaniel?
What I have not found in the literature is what I would call the equivalent of an antenna beam pattern for what happens. So the ray goes from WWV up to the ionosphere, hits the ocean in these areas. What I haven't seen in the literature is what I think of as the antenna beam pattern for what happens to the radio wave energy as it's been scattered by the sea surface. So much of it will be in the forward direction. And of course, that becomes our conventional second hop propagation down to South America.
Yeah.
So that's going to be most of the energy will be forward propagated, almost reflected as if there was a mirror. But we've got a rough surface. It's not a specular reflection. There will be some scattering in all 360 degrees.
It must be very little, and does it depend on the size of the waves?
You'd think so, yeah.
Surface roughness comes into it, and then what comes into the waves a little bit later is resonant Bragg scattering. And we can test for that as well.
Well, the COSAR radar system uses that. Maybe able to find some information from them.
Absolutely, but many of those the CODAR HF radars operate using surface wave, and not over a 2,500 kilometer outward path and a 2,500 kilometer return path. But yeah, the principle is well established. Crombie in 1955 wrote the paper in Nature about resonance scattering from ocean waves at HF. But the directional pattern, what I like to think of as the antenna beam pattern of the scattering, I've got no idea what it looks like. I suggest it's strong in the forward direction, but some does get back. And that's the cause of the fuzziness. And the cause of the fuzziness is that it isn't from a single point, it's distributed. So rays at different azimuth angles from WWV will find their way back via a path to Nathaniel. That's why it's fuzzy. It isn't a single path. And then I'm going to scoot down here. So when one looks at a time series of Doppler shift and amplitude. So the amplitude is in orange. So the graph of amplitude that goes with the plot, Mary Lou, is in linear units, but I've processed the data to get them in dB. And we see that there is, I think I made it a 38 dB down from the 1-hop signal level up here to the 2-hop side scatter signal level down here. 38 dB down.
That's quite faint, isn't it?
It is quite faint, but it's a very steady level. And I think that's the central limit theorem on our side, because there are so many individual rays of different azimuths and elevations over that area, contributing to the total signal level. We have that. So we have a form of averaging over many rays in terms of the amplitude. So it's very low, but it's very consistent. And then the eclipse has passed, the critical frequency goes back up again, and we shoot up to a very similar level as before. So you've got to be careful interpreting the Doppler, because there's 1-hop Doppler there before the shading, and there's 1-hop Doppler after the shading. And this Doppler within the region comes from that complex 2-path, one of them over the total eclipse. And so we have the 2nd hop and the 1st hop.
Your graph is going off of my screen.
I'm sorry?
Your graph is going off of my screen. It was expanded a bit too much.
No, it looks good here.
Yeah.
So anyway, just to get a quick update that so far I've just been doing some thinking. Sorry, I forgot one bit. Forgot one bit. Those squiggles. Those squiggles.
Little clocky things. What are they about?
Yeah. What they are about is this. So you don't really see it on a 2D ray trace, but when you do a 3D ray trace, and you plot the ray elevation angle, what distance does that reach? So, we all know that low elevation rays, so down here 6 degrees, travel further than rays at 8 degrees. But as you raise the elevation angle, it's not monotonic. You reach a ray elevation angle, after which a further increase in elevation angle gives rise to the ray landing spot being at a greater distance. But the slope is much greater, and then after that elevation, the ray penetrates the ionosphere and is lost to space. So we have 2 values for rays from 2 different elevations arrive at the same distance. Now, imagine this, if I call it a nose, imagine this nose to be at a much shorter range, over here somewhere, well off. Then at Nathaniel's location here, this distance, we've essentially just got the low rays. The amplitude of the high rays would be very small indeed. And now we'll move the nose out to this position, and the amplitude of the high rays increases, but the separation of them is quite substantial in terms of ray elevation. So the phase path that they've traveled for the high ray is much greater than for the low ray. It's penetrating higher into the ionosphere, and the phase path for the high ray is greater. So with the Doppler shift is different. And now we're going to take this nose, so there'll be a part in Doppler space. And now we're going to take this nose and move it right up to Nathaniel's distance. So the high rays and the low rays now are virtually the same in elevation. So there's very little difference then in their Doppler shift. So what we have, as this pattern moves to the right as the critical frequency decreases, i.e. we're being affected at the start of, start mid of the eclipse, this pattern moves to the right. We'll have two separated traces that then come together. Now, when the critical frequency rises after the passage of the eclipse, this nose, which is out here somewhere to the right, moves here to the left. After the eclipse, the nose has been to the left, and I'm getting confused now. Sorry. Now, as we move from the eclipse phase to the no eclipse phase, this nose is off to the right. So the first thing we see as the nose moves towards Nathaniel's location is this part of the nose. So where the high and the low rays are very close together, very little difference in Doppler shift. And then as it continues to move to the left, we have greater difference in Doppler shift, and then the high rays amplitude will decrease as it continues to move, and it'll fade away. And when we look at these little squiggles, when we look at these little squiggles, we've got Doppler that's apart and then comes together. So that's like the nose. We're right on the nose just before the band closes, as the critical frequency has dropped so far that one hot propagation isn't possible. They come together. And then as propagation comes back, they're together, and then they part. And then the top one then has faded away quite quickly, and that's the high ray. So the high ray is up here and the low ray is down there. So that's likely the cause of those squiggles, and two hot backscatter is likely the cause of this fuzzy low amplitude trace. So and the next stage will be to do some analysis, further analysis on the actual data to see how they fit in with those ideas on propagation. But there's an awful lot in that image.
Gwen, can you put up the picture again with the nose in it?
Yeah. That one. Yeah. Yeah. That one.
You have to share again, I believe.
Oh, sorry. Okay. Yeah.
Now we're seeing it.
I think this is fascinating. But I would ask you in Tufty's honor, if you could make this diagram again, or the next time you make this diagram, could you make the sizes of the dots corresponding to the amplitude? Please, please.
Oh, well, the sign of a good teacher is one that stretches their students. So thank you, Mary Lou, for that suggestion.
But then you can see the big dots become little dots and fade away.
Yeah, I'm okay. I'm going to have a cheats way around this. I have yet to learn how to extract the amplitude of the signal from PyLab. Okay, so I will endeavor to do that.
So ask one of Nathaniel's students. I suspect
Yes.
Nathaniel himself will be busy for a while.
Indeed, exactly. Um,
I
a-
expect it's got to
a-
have a model for the path loss.
I'm sorry?
It's got to have a model for the path loss.
Yes. Yes, I mean, you know, the model is in there. It's my lack of knowledge on how to extract it within PyLab.
Hey, Gwen,
Yeah.
my request is a lot easier and simpler. Is
Okay.
this, did you put this on the HamSCI website, or is there a way that we can, or at least that I can have a chance to go through and understand it better and look at it?
Yeah, I mean, I can do that under this the theme, you know, one of the posts of this science meeting. It's so, you know, work in progress, Ron. I tend to, you know, do these detailed notes as I go along to try and clarify my thoughts. It's probably been obvious at a couple of points this evening that, you know, I need to say this out loud several times so that it's clear in my own head what's going on.
Well, maybe you could even, maybe Gary could even just put it on one of his emails that just goes to this group that
Okay.
I would like to look at it.
Me too.
Being
Yeah.
quite honest, I understood at a low level what you were talking about,
Hmm.
but I would like to understand it a lot better. And having the document that I can use other resources, either other people I can ask or I can look things up to understand it better. So if you would do that, see, I told you mine was a simpler request than Mary Lou's. So
Oh no, it is, and you know there are footnotes. This is the 11th footnote, for instance, this one. So you know a way to follow up the argument. Yeah, the simple proxy, Mary Lou, is that the spacing of these dots is related to the amplitude. So okay, so that's a proxy which Kevin Davies in his book does call upon. So I thought that was a sufficiently good authority. So it's a proxy, but you're right, it would be really nice if I did have amplitudes.
Yeah, I'm finding interesting to look at in the personal space weather system graphs where they have the green graphs, which you just showed, which give the Doppler shift, and then they have the blue ones for amplitude.
Yeah.
And interesting to look at them in separately.
But it's hard to make much sense when the dynamic range needed is at least 38 dB as we've got here, or when it's on a linear scale.
Right. Right. Intriguing. So it'd be interesting also to know. So
Yeah.
you should have one of your students or colleagues, whoever, have them look up what the weather was like in the Gulf of Mexico on eclipse day.
Yeah. But the weather isn't actually a tremendous determinant. So this is something for me to then look at. So
Well, the surface roughness is playing into this in a big way.
well, it's
Small way, just a small way then.
small ways. The Bragg scattering is will be, if it's there, will be at exactly plus and minus 0.51 hertz from the main peak. Okay, because it is the phase velocity of C waves with a wavelength of half the radio wavelength. So 25 megahertz, radio wavelength 12 meters. So it's the 6-meter long waves that will give you resonant Bragg scattering. And those 6-meter long waves have a particular phase velocity, which is constant in deep water. And so we could say with certainty where to look for sidebands on the Doppler shift.
That's good. I like that part.
Work in progress, yet to be done.
Yeah, and if we had some ship out there that was sending things by sporadic E to some other ship, who knows?
Yeah, well, your National Oceanic and Atmospheric Administration, as taxpayers, you are paying them to have a whole multitude of buoys out in the Gulf of Mexico. All that data is easily available.
Very, very cool.
They
Oh.
really have had waves that big in the Gulf of Mexico. I didn't think the
Sorry,
waves were that high.
sorry, the 6 meters was the wavelength, not the amplitude. It's the wavelength of the waves that's important. Effectively, it acts as a diffraction grating
Oh, okay.
for the incident radio waves to then come back.
Okay. That I can believe.
Yeah. Sorry, a lot of these concepts are perhaps not immediately on hand to us as radio amateurs. They're there in particular narrow branches of RF applications, such as high frequency CODAR radar. But in normal life, these don't impact us at all.
Mm.
But this is a nice data set.
But you study this in physics too. So
Bragg scattering, yeah,
there you
yeah.
go.
yeah.
This is way cool. Right. So we will have, Gary, no meeting next week, correct?
Correct. Yeah, the holiday next week.
We're all going to watch fireworks or eat hamburgers and hot dogs or some such.
Or both.
Or both. Right. Or wave flags or go to parades or anything. And Gwyn will just have to, well, not do that. Any rate. And then we see
Speaking
you
of-
again in 2 weeks' time.
Right. And speaking of sporadic E2, we are getting some speakers lined up. Gareth has been hard at work. We've got a few others. Gwen's worked. We've been working with Chris Deacon. So between roughly the 11th, the 18th, and the 25th, we probably will be having our sporadic E discussions as well. So.
Hey, Gwen.
Yeah.
Hey, Steve.
This is Steve. That was fascinating. Great work. Is this geometry for getting the 2-hop side scattered? Was that unique to the eclipse, or is that something you can do any old time?
No, you could do it any old time. And my poster at HamSCI in Cleveland was about 2-hop side scatter on a north-south path, Oregon down to California, on 14 megahertz, where that path is always in the skip zone. And so propagation was only by 2-hop side scatter. And when you've got a north-south alignment, rather than east-west, which is what we had here, when you've got north-south, the intersections of those circles, you have 2 of them, one to the east, one to the west. And in the morning, it's the propagation to the east that matters, the intersection. And they swing through during the day where the intersection happens to the west. And that's a fascinating data set, Oregon, California, because to the east, it's backscattering off land. And to the west, it's backscattering off the Pacific. So, I mean, what always intrigues me is that as radio amateurs, with the community of people that we have, we can do these experiments under fairly controlled conditions. Like we could have a coastline, so we have land in the morning, sea in the afternoon. And for that poster, a friend of mine, WB7ABP Lynn in Santa Rosa, California, has a 6-element beam for 14 megahertz. So he rotated the beam to show that the signal peak was indeed off the Pacific in the evening, and the peak was not when his beam was aligned up to Oregon.
What I was going to offer as a suggestion, especially with WWV,
Yep.
making both absolute and relative time of flight measurements is really pretty easy using the timing ticks.
Right.
That side scatter path is twice as long as the straight shot. I can show you a picture of simultaneous WWV and WWVH. They're on the same frequency. So you see, here is the pulse from WWV. 17 milliseconds later, here comes the one from WWVH.
Yeah, I've seen
If
that.
you had a GPS DO, you could make absolute time of flight measurements. But even if you just look at it, you can get relative and just look at the difference. And that's easy.
Yep.
And that would conclusively prove that you had a path in there that was twice length.
Yeah, that would be terrific. It's bringing the people together with the the knowledge, the relevant expertise, and the equipment to be able to do these experiments, and that's what's great about HamSci for me, anyway.
Yeah.
About 5 years ago, I did a bunch of these time of flight measurements. Pretty easy to do. Just all you need is an oscilloscope, and if you want to make absolute measurements, you have to have a GPS DO with that rising edge, which goes positive at exactly the instant that timing tick leaves the WWV towers.
Right.
It makes time of flight. Once you calibrate out the delays through the DSP radios, you can make absolute measurements. Anyway, just a thought.
Yeah. No.
Well, good. It sounds like we've got some more things to keep us busy. We don't have to wait for the next eclipse, it sounds like. So we've got some options.
This is just looking at one plot. One plot. Oh, it's a lifetime's work.
Plot thickens.
Or we need more graduate students, one or the other. I'm not sure how that works. Mary Lou says yes.
There's one right there. And she's smiling.
So, all right. Well, very good. This has been a very interesting call. Gwen, thank you very much for that. And
Yeah.
and we're not done with it yet. We've got more to go and we've got more to learn yet. So that's encouraging too. So on my part, I'll keep working with others to get the sporadic e-discussion set up. Gwen's got his hands full and is digging in deeper, I'm sure, on the 25 megahertz side scatter questions. And Mary Lou will keep looking at graphs too. And hopefully we'll get a few more recruits. You saw I did the posting to the grape group.
Yeah,
I'm
I
not
just
sure if
did
anybody
another 24, so I want to tell you about those sometime, but not now. So Gwen, you send us this write-up you just had and send it to Gary. He'll send it to all of us. Excellent.
Yep.
Very cool.
Thank
Very
you. That's
Yeah.
cool.
Yep.
Okay, all right, we're a few minutes past. It was well worth it. One of the things I want to say, you'll see go up in the HamSCI. I'll make an announcement for it. I've got the all the results done from the Gladstone Signal Spotting Challenge of 2024. And everybody obviously welcome to read as much or little as that as they want. But the one thing I want to say is to if you do go on to it and look at it, take a look at some of the comments from the participants. There are some people who really appreciate the fact that they've got a chance to contribute to science and seem very interested. A few people did a little of their own analysis on the whisper signals that they receive them and so on and so forth. So there's plenty more of us out there, I guess, but exposing all this to the wider, greater amateur community, I think is very, very valuable. People seem to enjoy it and appreciate it. So maybe I'll bring a couple of those comments up next week because they do pertain as well to some of the people that are here. So. Yep.
One more thing, thinking about communities. So the amateur astronomy community is now waiting for developments. There's a star which is going to explode sometime this year, sometime from July onward. Now it's called T Corvor. It's a recurrent nova, and any day now you may read about it in the newspaper. And I've got amateurs taking measurements of it every clear night. To-doop, whoop! Not yet, not yet.
Is that one of those things where it's exploding now, or it happened, X number of light years ago, and the light's only reaching us now? Is that?
Oh yes, well it always is like that. So 2,000 years ago it exploded. We should get the light sometime this summer.
Yeah, I'm calibrating my mind to that idea. So
this one does it every 80 years, more or less.
Wow. Excellent.
Anyway, whatever.
Okay. Any closing comments? We'll shut it down for this week and we'll see y'all in 2 weeks. Have a safe 4th of July week and hopefully everybody's got some holiday time. They can enjoy themselves next week. So, and no
Thanks.
classes and no exams. Nope.
Yep.
All right. 73 all.
73.
All right.
Thanks, everyone.
Bye-bye.